Okay, everyone. So we had the test yesterday, and today we're just going to continue on with the next section, 2.3. So we're continuing to look at the derivative. So at the moment, what we have for the derivative is just like a slope, the delta y over delta x. So the notation we've been using is like f prime of x. Which we should think about as the limit of delta y delta x. So another way that we use to denote the derivative is dy dx. So instead of the deltas, they use the d's. So that just, when you do that, you're just saying it's kind of like the same as using the delta, but you're also at the same time saying we're taking a limit. So we're making it as small as possible, so as small enough so that we get stable answers. This is known as the Leibniz notation. You don't need to know that really, I guess. Just that if you know the people who invented calculus back in the 17th century, there was a German guy, Leibniz, and there was an English guy, Newton. And so that's why a lot of times we have different kind of notation. But that's beside the point. So the reason why we like to, so this has different advantages, these notations. So when you use this notation, you're thinking of it as a function. So remember, what do you need for a function? You just need a rule to turn an input into an output. And this is just saying, okay, what is the instantaneous rate of change at that? So you can put in a number, so you can talk about f prime of 1, for instance, or 2, or whatever. Here, this is kind of more like, you're thinking about it like what we call an operator. So you think about this as d dx acting on something. So that means like taking the derivative. And you can do that sometimes it's, you've got an equation and you think, well, let's take a derivative of this equation. So you can with this notation. If you want to turn this into a function, you've got to do something like this. This just means take the derivative. This just means evaluate at x equals 1. So this is just some notation you might see. So don't really get confused by that. Okay. An important thing that I'm going to emphasize, and whenever you're given a question that has units in it, units should be part of the answer. So units are important. So the question is, what is the units of the derivative? Well, we can see that when we look at how we define it, right? We think of a derivative as a change in y over a change in x. Well, the units of change in y are going to be in the units of y, right? If we go from 2 feet to 3 feet, the change is 1 foot. And the units of delta x, so this is also the units of dy, these are the units of dx, is units of x. Right? If we change from 0.2 seconds to 0.3 seconds, the change is 0.1 second. So the units of f prime of x are the units of y per unit of x. Right, so if y is in feet and x is in seconds, then dy dx is in feet per second. So does that make sense? Right, so if we talk about distance with respect to time, the units is feet per second, which is a unit of velocity. So whenever you're asked a question and it's talking about something, you should always make sure to put the units in there. What happens if our y, instead of talking about feet, let's say y is velocity, and it's going to be feet per second. So what do we call the change of velocity with respect to time? Anyone remember? This is too early. Anyway, what is the units here of dy dx?
Feet per second squared.
Feet per second squared, exactly. It's feet per second, which is the same thing as feet per second squared. And what's this units of? It's acceleration, remember? So, yeah. So acceleration is the rate of change of velocity. Let's say you're studying trees. Okay, let me draw a tree. We're studying trees and we're interested in the weight of the tree. Let's say W in pounds. And as a function of X, which is the height of the tree in feet. Okay, so what is W10? W of 10. What does it mean? It's going to be a number. It's going to be a certain number of pounds. What amount of pounds is that going to be? It's the weight of a tree, which is 10 feet tall. Exactly. Okay. And so we could, if we were some kind of forester, we could make up a table of different trees at different heights and their weights. Okay. So this is in pounds. What's the derivative of W at 10? Tell us. So, well, firstly, what's the units?
Pounds per feet.
Pounds per feet. Okay, that's a strange little ratio. Well, what does it mean? Well, what it means is you've got your table of weights of trees at different heights, and it's basically saying, well, if you think of the tree growing, you know, growing in height, growing in weight, so it's how much the tree is growing when it's 10 feet tall. So it could be like, I don't know, 200 pounds per feet, which means that when a tree is 10 feet tall, it's gaining weight at the rate of 200 pounds per foot. So if we had that W10, let's say is 2,000 pounds, and W prime 10, let's say, is 300, what would you estimate to be the weight of an 11-foot tree?
Around 2,300.
2,300, exactly right. This is this same concept of linearity that we saw before. So when it's around 10 feet, it's gaining 300 feet per pound. So we would expect an 11-foot tree to be around 2,300 pounds. We would expect a 9-foot tree to be around 1,700 pounds. It's not going to be exactly that, but this is an estimate just brought about. We're just assuming linearity, which is what we're always going to assume. Hang on. Since I'm zooming this, some people have to not be in class. I'm only going to be using one half of the blackboard, so I have to rub that up. So can I rub this off? Okay. So let's do another example. So I know none of you use Facebook, but let's pretend that you do. Okay. So let LQ be the number of hours you spend on Facebook per day when you have Q friends. Okay, so what does L of 15 represent?
The number of hours you spend on Facebook when you have 15 friends.
Exactly. So what would you think that would be around? Someone's best guess.
Like 2.
2?
An hour or 2?
Yeah, let's say 2. So it's 2 hours. And so this means that you spend 2 hours on Facebook per day if you have 15 friends. What does L prime of 15 mean? Okay, it's the rate of change. So what is the change in the number of hours you are likely to spend if your number of friends change? So what would be a guess for that to be? So it would be what? It'd be something hours per day. No, hours per friend. No, sorry, it's hours per day, because that's the units of L, per friend, because that's the units of Q. Okay, and so what might be let's say 0.1. What is this statement saying? What does that mean?
You spend 0.1 hours per friend per day on Facebook.
0.1, it's the change though. It's the additional Hi guys. Did I get lost for a little bit? Oops. Anyway, where was I? Oh yes. So it's doing this calculation for us. So that means then that delta y is approximately f prime of a times delta x. So this is the equation in a different way. Okay? Just by crossing off. So you can see it's the same thing here. But you see that this is exactly what I did over here. Okay? So we can see another interpretation of the derivative is that it's a multiplier. And by a multiplier, I mean it turns change in x into change in y. Okay, now what's delta y going to be? Well, delta y is something kind of like, what is it? It's going to be, y minus f of a. That's the definition of what change of y is. It's approximately going to equal f prime of a times delta x. So that tells us that y is approximately f of a plus f prime ax. That's exactly the slope-intercept form. And this is exactly what I did over here. So this is a way of making approximations. So this is a way to make linear approximations. So if I know what the value of a function is at a point, I know what its value of its derivative is at that point, I can estimate what the function's going to be around that point. And just like over here, it's best when we're close to the point we started with, our base point. But it's good because we can use this to make approximations, which can a lot of time be useful. Okay. Another thing. Let's get rid of this. So I've been talking about rates of change. Another useful thing to talk about is relative rates of change. And so by relative rate of change, I mean, so the relative rate of change of a function f at a point x at a point A is, well, it's the derivative of A. So remember, this is the linear, this is something linear, right? It's the rate of change that you get from the tangent line. And then you divide it by f of A. And so the useful thing about this is you sort of get out the units of the y, right? Because the derivative of this is units of y per units of x, and the thing of this is units of y. So when you divide it one by the other, you get rid of units, right? So you get like, so this is when you're talking about percentage change. Okay, so for example, if what was an example? What was the example I had before? So I said that L prime of 15 was 2. Oh no, L of 15 is 2, and L prime of 15 is 0.1. So this is kind of like an absolute change, right? It's hours per friend. Whereas if you look at the relative rate of change, it's going to equal 0.1 divided by 2, which is what? Is 1/20th is 5%. So that means that when you've got 15 friends, the amount of change of the time you spend on Facebook is 5%. You spend 5% extra time when you've got an extra friend. Sometimes that's a useful way of talking about things, talk about relative rates of change. And it's particularly useful later on when we talk about exponential things, because we know exponential things have a constant relative rate of change. And we'll get that at a later time. Right, so remember, constant relative rate of change is exponential. So in these situations here, if the absolute rate of change never changes, or let's say it's always 2, for instance, that just means we have a straight line. That means we have something linear. If the relative rate of change never changes, that means we have something exponential. We've got something that grows at 5% each time. Are we doing good? Oh, we're doing good. Okay. Let's do another example. Let's say we've got a function C of R, and that is the cost of paying off car loan borrowed at 5% per year. So C of R represents the total amount of money that you gave to the bank for your car loan when the interest rate is R. What are the units of the derivative of C of R? So what's the units of C? how do you usually pay off things?
Dollar sign.
Yeah, it's dollars per what?
Percent of interest rate.
Yeah, dollars per percent. Okay, it shows you. So what does that mean? Okay, so this tells you kind of like the extra money you pay as the interest rate rises. Or from the marginal point of view, it's the extra money you pay back per percentage point per increase of a percentage point of interest. So I have these two things, C5 and C prime 5. So what's C of 5?
Extra money, pay back for 5%.
Nope, nope, that's not extra money, it's C of 5%. So just read the thing there. It's the,
Cost of paying off Carl and borrowed at 5% interest rate.
it's the total money back at rate of 5%. So the extra comes in the derivative here. So this is the marginal cost. So the extra money paid back if rate rises 1%. Right. So C of 6, for example, is approximately equal to C of 5 plus C prime of 5. And C of 5.5 is approximately C of 5 plus a half C prime of 5. Okay, let's do just one more. Let's say we have a population. P of t at time t. And let's say we have, so this is in millions, let's say. And let's say P of 2011 is 37.65. And P prime of 2011 is 0.4. Okay, what do these numbers, what does this mean? What does this mean? Have we go, what does this mean, this statement right here?
population during 2011?
Right, in 2011, the population was 37.65 million. What does this tell us?
Its population growing or something?
So it's a derivative, so it's the rate of change. So it's how the population is changing at 2011 and how is it changing at 2011.
5.4.
Right, at 2011, the population was growing by 0.4 million per year. All right, so in 2011, this place had 37.65 million or 37,650,000 people, and it was growing at the rate of 400,000 people per year. Okay, so what would the population be in 2013, you think?
$38.4 or $38.45.
Yeah, 38.45. You just took this and added twice that, right?
Yep.
Yeah. So a million. I forget the million. Exactly right. And what is the relative rate of change in 2011? Well, it's 0.4 divided by 37.65. Can anyone go calculator for me, please? Let's see, you got that.
.01.
0.01.
Yep.
Okay. Or, and I'm putting it another way, in percentage terms,
1%.
yep, it's growing at 1%
Per million per year. Or
per year,
per year.
right? Because it's